So give a little bit more introduction. Let me pass out these. I have got a few little fun items to share. You know, to take on their combinations. Help me out actually. And those back, Miles. These are 4 gigabyte thumb drives with a bottle opener on it. Here I also have I've got stickers. I've got small little door prize at the end. I guess raffle off somehow. If you want stickers, I'll put these up here. You guys should grab them. So I work for a small company. This is software. We're startups. We're built on Ubuntu Linux, like I said. My background, I'm a software engineer, so that's where this talk is coming from. That's where my security background is. So I'm not a security expert. I'm not about to go design a new encryption algorithm, some new Cipher. I'm a systems developer. It's my specialty. BYU, I did a master's focusing on distributed systems at Stanford, so that's kind of where I come from. We build web applications with my current company, so that's where the perspective of this talk is. How many people are software engineers here? I'm quite sure. Most people. Some people are like network engineers, DevOps. You used to do DevOps, right?
DevOps, everything.
Okay. We got code in here. It's like most of our software engineers, so hopefully it's helpful examples. Cargo cult security, I'll explain the name a little bit, start out with. It starts out with cargo cults. Have you ever heard of cargo cults before? Yeah? So this is an example of a cargo cult phenomenon that was observed since the 1800s and was really popularized after World War II. It's a phenomenon these anthropologists saw happening where primitive societies would suddenly come into contact with industrial modern societies. So it happened, of course, in World War II in the Pacific, where Imperial Japan and the United States were battling to build airfields and bases and ports in these remote islands in the Pacific. And these native people suddenly came in contact with them and started to have access to some of the goods they brought with them, which is jeeps and gasoline and rifles, canned food, and all kinds of really interesting cargo. Well, when the war suddenly ended in 1945, these primitive people wanted to be able to still receive these goods they'd experienced for several years. But of course, the industrialized nations just abandoned their airfields and such in most of the places. And so what they did is started to build bamboo airplanes. And you can see right there, people actually would sit inside of wooden and bamboo towers with little wooden headsets set on their ears. And it was a form of sympathetic magic or imitative magic where they were trying to get the same benefit that they'd seen these military societies or military organizations bring by practicing some of the same practices that they'd seen these people perform, such as building landing strips and having airplanes, sitting in radio towers, and even marching around in uniforms. Of course, that didn't work, right? That was not the causal effect for cargo dropping from the skies. The cargo gods were not actually going to give cargo by doing this, but they've done this and it's been observed many times. Well, in the 70s, Richard Feynman, the Nobel Prize-winning physicist, popularized the metaphorical use of the term cargo cult, called cargo cult science in a university commencement address, referring to science that has the form of science but doesn't contain real scientific integrity to it, not real scientific research. And of course, computer scientists took that term and talked about cargo cult programming, which is the ritualistic inclusion of code or patterns that are unnecessary for the task at hand. It's often, we often do this, perhaps junior engineers or even more experienced when a new system will see a pattern and will copy the pattern. It's not a bad way to do things, right? It's often the way we learn. But sometimes we apply the incorrect pattern that is not the causal effect that got some benefit we're searching for. And these are some I picked out. You probably have your own pet peeves in code. Design patterns can be overused. The factory pattern. I can't just new up an object. I need a factory for it, so I'm going to create a factory just for factory's sake. Or a wrapper. Do we have any Java developers in here? A few. So I spent several years in Java, and I like it. We use a Java JVM-based language in my current work. I feel like the wrapper pattern. You don't want to encapsulate something, so you got a wrapper to it, and you got a wrapper to that, and you got a wrapper to that. And suddenly you have Java logging. I never understood Java logging to save my life, and it's just like 5 layers of wrappers. Dependency injection is another one. Commonly used, I use it for my unit testing, but sometimes engineers seem to add dependency injection because that's what you do, not because it meets specific need. Cryptography is another one. We'll get into this. Any other ones people think of? Maybe you'll list those examples. Overused patterns. Anyone seen them? One in their work? Well, pet peeve time.
Singletons can be.
Singletons? Yeah. People create a singleton.
For no reason. Especially if you can go back off the core system.
The core?
Yeah. If it already had the capabilities of setting something, you can use the same process. At least in PHP and Magento. So
that's kind of like a factory pattern, right? Create a factory, singleton. Overused. Cryptography, so that's the topic today. So that's where cargo cult security comes in. People I've seen often add encryption because what they want is security. And they see, well, I understand that most people, when they want some security, they add encryption, so that's what I'm going to do. Or hashing, same idea. So we're going to talk through some examples and see correct and incorrect uses, mostly incorrect uses, that's the fun part, of cryptography. The big picture, this is your threat model. So I'm kind of coming at this, like I said, from the perspective of developing web applications, so network-based systems is kind of what I'm assuming is our platform here. So we have some client, and we have a server, and they're what we want to communicate between, but everything else in between is controlled by an attacker. So the network at evil.org can do anything inside the network. They can read or view messages that are sent. They can duplicate messages. They can drop messages. They can modify them. They can fabricate them out of thin air. They can do whatever they want. The attacker controls the network. So we still need to be able to operate in this environment securely. There's several cryptographic primitives we can use on the top here, and several security goals that are very different. One is data integrity. Did the attacker modify my message transmission? Did authentication? Who sent it? Did the individual send it? The client send it that they say they are? Non-repudiation is, can I assert that a certain entities created and generated this message and prevent them from lying that they sent it? Confidentiality, that's usually what we think of when we think about security, the secrecy. It's a common one. And then trust. I talked about digital certificates here, and I actually took this table from a talk by some Veritone engineers. There's a link to this talk if you want to see this filled out. So in the talk by these Veritone engineers, it was a wonderful talk, and they filled this out very methodically. I'm going to kind of take it from the anti-pattern perspective and the cargo security perspective. So we'll talk through just a few select anti-patterns. So how do we achieve these goals? There's some different tools we have. There's hashing, and then building on that, there's message authentication codes or hash-based message authentication code. You've probably heard of HMAC SHA-1, the most common one used. Symmetric key cryptography, that's classic encryption. Asymmetric key cryptography or public key cryptography, digital signatures and digital certificates. So let's talk about how these can be used and inappropriately applied. Starting with the classic one. That's perhaps the most overused, improperly used one. Like I said, we want security, so we add cryptography or we add encryption. Well, it's not really true. I will define some terms first of all, tell them a story. So does anyone like history like me? Yeah, history. I'm not necessarily super knowledgeable, but I love it. I find it fascinating. So you see here, January 19th, 1917, World War I's raging in Europe. Woodrow Wilson has kept us out of the war. He ran on that, on keeping us out of this European conflict. And Germany is wreaking havoc on the world with their submarines. Now, the U.S. is an independent nation. They're not involved. They don't want Germany sinking their ships. They're theoretically neutral, even though there's a lot of sympathy in the United States for the allied powers of France, Russia, and Great Britain. Well, Germany had paused their unrestricted submarine warfare or attacking any ship that was, for example, doing business with Germany's enemies. They stopped that for a while, but they were about to resume it, and they thought, well, this might cause the U.S. to enter the war against us, because the U.S. isn't going to like it. We start torpedoing their merchant ships. And they said, hey, what if we can open up a new front to the war on the U.S.'s border, if that happens? So they actually sent a telegram from the German foreign minister, named Zimmermann. Zimmermann telegram. Does that sound familiar to anyone? Yeah. So Zimmermann sent a telegram to the embassy to be delivered to the government of Mexico, proposing we intend to begin the 1st of February unrestricted submarine warfare, and we expect the U.S. to enter the war, and we want you to be our ally. If that happens, and what we promise you is we'll help you recover lost territory, Texas, New Mexico, and Arizona. That's not something we want to hear in America, right? Well, the British foreign intelligence intercepted this message, and they were able to decipher it. And of course, they were just ecstatic that, hey, we can use this to try to pull America into the war on our side finally. They happily turned it over to the Americans, showing them what Germany was trying to do. And sure enough, just a few months later, we ended up entering the war on the side of Great Britain. So this is the telegram that was sent, intercepted, and this is the message, and then this is, you can see the actual British intelligence officer's handwriting there as they're deciphering this message. Here we have, Mexico, Texas, Mexico, AR, and some other words there. So what this means for us is we're going to talk about ciphertext, ciphers, and plain text tonight, where ciphertext is plain text that has been encrypted by the use of an algorithm called a cipher. So we term ciphertext, ciphers, and plain text. Symmetric key cryptography today, modern cryptography, modern encryption, there's several algorithms, common algorithms. Blowfish, AES is the one most people use today that you've probably heard of, or the Rindall algorithm. Example applications that use it, HTTPS, HTTP over SSL or TLS. SSH, secure shell, we're all familiar with. Anyone familiar with LUX disk encryption? Use that? Yeah. So we use that at Lucid. It's a way to encrypt volumes of disks, so having encryption at rest of data. KeyPass, anyone else use that? It's a fun one. Yeah. So I use it to track my passwords and encrypt passwords. And KeyPass, all these applications use symmetric key cryptography, at least in some part of the applications. Let's talk about examples of using it and how we might use it and how we might want to use it. Blowfish, we'll use an example with Blowfish, but this could be applied to any symmetric key cryptography, really. We have some plain text. Keep it secret, keep it safe. Anyone else going to go see The Hobbit? Excited? I'm excited. Ciphertext, we turn this plain text into ciphertext with the use of a cipher, right? So here we use Blowfish. I got some PHP code here. I forgot to mention all these most of these examples I've got on GitHub. If you want to go play with them yourself, not super nice web page. I've got little PHP web pages you can go and play with this code and try out some of these attacks yourself. So we got Blowfish. We've got a secret key. All familiar with that idea, right? There's a plain text, and there's two other parameters which we'll talk about later. But it's a mode and an initialization vector. So you can just ignore those for now. We'll get into those. But we have Blowfish, so symmetric cryptography, a key, and our plain text turns into ciphertext, and we're going to print that out. And this is actual deciphered version of keep it secret, keep it safe. Some information security there we have from that message. Let's look at an anti-pattern with this library. How many people have tried sharing a Google Doc by sharing a link? So not common, right? You can go and generate a secure link, a cryptographic generated link, and share that with someone without having to type in their email address. So let's see if we can try to implement that with encryption. So we're going to have some plain text ID. What we're going to do is we're going to share secure images in our applications. So we have plain text ID, perhaps 100,000. Maybe we have some auto-incrementing ID in a database generating image IDs. And we're going to print out secure URL for the image. We're going to serve the secure URL to the user. So we're going to encrypt it with blowfish, like we saw before. And we're going to tack it on as a query parameter, the encrypted ID. And so we're going to generate a link, href equals secret image URL, and give them the secret image URL. So here's the link, private image.php, secure ID equals, and some encrypted value for 100,000. How do we actually serve that image then using this code on the other side so the user can get that if they follow the link or share the link? The server is going to read the query parameter. They're going to decrypt it using the inverse. So there's decrypt, blowfish, we give it the key, and the ciphertext. We get our plain text out of it, and sure enough, it works. Gives us 100,000. And then we can go look it up in a database or file or whatever. We're going to look up image 100,000. And then we're going to stick it inside an image tag and display it to the user. Make sense? Mm-hmm. And what do we get? This is team image. There's our company image. That worked, right? Seemed to work. Well, let's try something. See what happens. Let's try flipping the last bit in the URL. Any idea what that's going to cost? Our code's going to happily read the query parameter. That's fine. Now what happens when we call decrypt on that? Any ideas? Anyone know the answer? Flip the bit into plain text. Flipping the bit in ciphertext, flip the corresponding bit into plain text. And suddenly we're serving Napoleon's secret plans for the Battle of Waterloo. That wasn't too hard to attack, was it? So what do we do wrong here? We use encryption. We've got blowfish. This is a pretty secure cipher. We're using a secret key. No one ever got the secret key. What happened? Well, the problem is symmetric key cryptography does not give us data integrity. Anyone can go modify that URL happily, and it will happily decrypt to very predictable values. And so let's look at what we can do. What we should be using is HMACs, or hash-based message authentication codes, for data integrity. We want to make sure, one of the things we wanted to ensure was that no one modified that URL after we served it to a user and was able to get someone else's image from that. So we can do something with HMAC. So let's dig into that. We'll come back to another fun example with encryption though. HMACs, there's actually an RFC for HMACs, RFC 2104. They're very commonly used. If you use Amazon Web Services, that's how they authenticate. And a lot of authentication and data integrity security mechanisms are implemented. The HMAC MD5, SHA-1, SHA-256, different hashing algorithms you can use for HMACs. And the idea is fundamentally you've got some message, and you want to make sure that no one modifies the message, so we're going to tack on a little suffix to the message, which is this message authentication code. And HMAC takes not only the message and its input into the function, but also a secret key. And the assertion is that without the secret key, it's computationally intractable for anyone to guess that message authentication code. So if anyone were to modify the message, they would not be able to generate a matching map. Here's some code to explain it. See it in action. So in plain text ID 100,000. Instead of encrypting it, we're going to create an HMAC of this plain text ID, where so the message is simply the ID 100,000. We're going to tack both the ID on in a query parameter and this message authentication code, and that's what we're going to serve to the user. So we get private image2.php, ID equals. Now, we're trying to serve secret images, but not secret IDs. The IDs probably are not secret here. That was probably just kind of a little mix-up on our part. The IDs aren't secret. 100,000, who cares? That's something we generated. It was something the user didn't even give to us. So we can go ahead and put that in the URL, and we'll give this HMAC at the end. On the other side, let's see what happens if an attacker tries to flip a bit here and get image ID 100,001. Our server is going to get the ID from the query parameter, get the message authentication code from the query parameter. It's going to recalculate the HMAC based off of only the plain text ID. It's going to compare it to the one passed to it. If they're equal, then we'll go ahead and serve the image. But since they're not equal, the user modified it, we're going to give them a permission denied error. Any questions about that before we move on? Makes sense what we're doing with HMACs, message authentication codes? So that's a secure way to do it. That's the correct way to provide data integrity, is to use HMACs. That's the tool in our tool belt we want to use. Let's look at one more with encryption. It's a really fun one. Let's say instead of serving it, just to look at this from a different perspective and different attack, we're going to pretend we're going to do something very similar with serving a secret image, and we're going to use a user ID, 834. Again, we're going to serve a secure URL for the image. We're going to encrypt it with, this time I just picked AES, Rindell algorithm, 128-bit block. Here's our user ID. We're going to encrypt that, tack it on here, and let's see if there's another way we can attack this incorrect use of encryption. So we're going to serve this secret image to the user now. And what we've done here, look, we've got 3 bytes of input and F3D90E. So and you see what we've done is we've hex encoded this. So what it turns out is this 3 bytes of input turns into 3 bytes of output. Well, why is that a problem? How many valid URLs are in that space? How many valid 3-byte URLs if we're assuming we've got some auto-incrementing user ID? There's 100, 101, all the way to 999. So there's 899 valid URLs, right? Well, that's only a search space. If we just, these 3 hex encoded bytes, it's a valid URL density of 1 in 17,000 chances if we simply look for secure ID equals 000, 0001, 0002. So 2 to 24 search space, not a very big search space. So the problem is we encrypted it, but we haven't necessarily generated a very big search space for an attacker to search through. They can just simply pound through, a few 100,000 URLs, make requests, and every 17,000th, which is not going to be every second, but maybe every hour, they can get a valid image from our secret service and reveal secret information. So again, we should not be using encryption for this application. These images are secure. We should serve them over HTTPS, but when we're generating these URLs, we're not actually protecting ourselves by encrypting these URL parameters. So HMAC for authentication, let's try that in correct use. First, we looked at data integrity before. You couldn't mess with URL. Very, very similar ideas, authentication. We can create these tokens for authentication. And this is actually what, like I said, Amazon does, AWS, and a lot of popular systems do. We're going to create this user ID parameter and a timestamp, for example. Perhaps this is a login endpoint where you log in and we're exchanging your username and password for some token that can be used for further authentication as you're interacting with the application. That's going to generate this token. UID equals 123 and timestamp is equal to some Unix timestamp. We're going to create an HMAC on that, HMAC of that message, tack that on to this to create a new token, and that's what we're going to send to the user, for example, set a cookie. How does that work? So this is our login endpoint, and our protected service, some secure part of our application, is going to read the token from the cookie. It's going to parse the message, parse this of the original part of the message, the user ID equals, timestamp equals. Like we saw before, it's going to read the HMAC, calculate its own HMAC, compare the validation HMAC against the signature sent to it. If they match, then we know that it really is user 123, and we'll let the request through. Otherwise, we send back 4 through forbidden. So this is the correct cryptographic primitive to use for something like authentication. Got that filled out there. One final encryption anti-pattern here is, this is my favorite one. So let's say it's my birthday and I got $150.01. I got some kids and they give me a penny for my birthday. And my wife gave me $150, I guess. I go to deposit it, and there's perhaps some teller, Sam, who's at a terminal, and they enter my deposit, and they accept the money, and they authorize the deposit, and they send the message that goes to the bank central server. Well, our threat model says that the attacker controls the network, so let's look at what could happen. The terminal is going to encrypt this with, here we're using AES encryption, Rindell algorithm, some secret key. It's going to encrypt this and encrypt the data and then send this message on where this is data. The attacker can modify messages, right? And they can read them. Now, they can't read the original message. They can read the ciphertext that's sent. They control the network. We've encrypted it, so we're safe, right? What the attacker's going to do in this case is they're going to take the 45th byte of this message and XOR it with the ASCII value, period, XOR it with the ASCII value of 0, and then change the 45th byte to be this new value. Let's see what happens in this case. The server of the bank's going to use AES to decrypt the message, and happy birthday to me, gobbledygook, amount has turned into $150,000. Happy birthday to me, right? Suddenly I'm $150,000 richer. What happened here? Well, this is an artifact. You can go this is actual working code I have on this GitHub profile if you want to play with it. So I'm doing some little magic I'm not telling you about with these modes and things, and that's why some of the attacks are a little bit different from each other, but they're still the same principle, is that we can predictably flip bits into plain text by flipping bits in the ciphertext. So what we did is the 45th bytes around here, and because of the way modes work, it's actually going to garble part of this message, but who cares? I don't care. And it's going to predictably flip this byte over here, and it turned it from a period into a 0. Pretty easy, right? All I had to do was that. So encryption, doesn't provide the data integrity we need. What is symmetric key cryptography good for? Not very much. Even though that's what everyone thinks about. It's not good for any of that, Jack. It's just good for confidentiality, and that's it. So if we're using it for anything else besides confidentiality, we're using it wrong, and we're not getting the security we need. That's cargo cult security. So let's look at these two other parameters I kept kind of glossing over. So we have a cipher algorithm, and the actual cipher we specify here, AES blowfish. Secret key, we're all familiar with secret keys. We have our plain text, data encrypts, and the modes. Let's talk about that for a little bit. There's different modes of encryption. And most ciphers we use today, or block ciphers, just the idea that, hey, we've got to encrypt messages, or strings, I'll say, of various length. And so it's just easy if we can break them up into fixed size bytes, like perhaps 128 bits blocks, and encrypt those as single blocks at a time. Our algorithms can be coded to operate on fixed size blocks, and we'll encrypt one block and another block. So the way we encrypt these blocks at a time can be applied independently of the actual cipher. So the Cipher-block chaining mode, electronic code book mode, output feedback mode, and we'll talk about what that means. The last one is an initialization vector, which we'll follow up on. So very simple. This is another fun example. It's on the GitHub page. File get contents. We're going to read some file, an image file, and we're going to encrypt it with blowfish. We're going to see what this does. But we're going to focus on this parameter here. We're using ECB mode, electronic code book mode. And we're going to write it back out and see how well we encrypted it. Blowfish is a good algorithm to use. The image. What is that? The Hobbit, right? And suddenly I've encrypted this, but the movie studios aren't very happy that it's been leaked to the press what the new movie is. So here's the original image that we encrypted. Now, where did we go wrong? The problem here is we encrypted it, and individual blocks in the message do have some kind of security, information security. I don't know. I can't tell what the original value of this block is over here, but repeated blocks all map to the same value in the ciphertext. So you can see on the face here, the purple, there's blocks repeated all over the place, the same color, blocks the same color, and they map to the exact same output value. file. And that's why it's called electronic code book mode. It's logically equivalent to having a giant code book, and this value maps to this value maps to this value, just do a big lookup table. Logically equivalent to that. Well, what can we do to fix that? And that's what the modes do. The recommended mode is Cipher-block chaining mode, which takes the output of one encryption pass and uses that as input into the encryption of the next block. What it does is it'll obscure patterns within the message. So that fixes our Hobbit example. And the last parameter, the initialization vector. Another history example for this one. It's May 20th, 1942, just months after the end of the war. The Imperial Navy stomping all over the islands in the Pacific. U.S. territories are being captured in the Pacific and islands, and the U.S. is just reeling. We're losing the battle in the Pacific early on after Pearl Harbor and the end of the war. Well, the messages, the encryption that the Imperial Navy of Japan was using actually was somewhat broken, and the Navy knew that. They had these code books out for a while, and they actually written new ones, but they were delayed in getting them to the fleet. And on May 20th, the U.S. intercepted a message saying that there was going to be a surprise attack on island AF, but they didn't know what AF was. They couldn't decipher that. So they had a brilliant idea. They kind of thought it might be the island of Midway. So they told the island of Midway to send out an unencrypted message that their water desalination units were broken. So they did that, sent out this message, and then the U.S. picked up another message, and an encrypted message from the Imperial Navy that said the island AF was low on water. Right? So suddenly they kind of narrowed in, triangulated, figured out which island AF was. And instead of it being an ambush on the United States base there, it ended up being the United States were able to get the ships there. It ended up being an ambush on the Imperial Navy, and major turning point in the war in the Pacific. And what does that mean for initialization vectors? Well, today, let's say Green Army is waiting to attack the Orange Army, or preparing to attack, and the Orange Army is wondering when they need to be prepared to defend themselves. And the Green Army is sending these messages to among their camps, saying, and they send the message, here's some code to encrypt the message hold. Well, the Orange Army wakes up on Monday morning, and the general talks to the radio operator, says, can you tell me anything as you're listening to our enemy? And they say, well, I got this message, but I don't know what it means, so I'm working on it. I'll try to encrypt it. Tuesday morning, the radio operator brings the same message to the general of the Orange Army. I got this same message. Day goes by, nothing happens. Wednesday, get the same message. Day goes by, nothing happens. Thursday, same thing. Friday, the radio operator runs in the tent of the general and says, I just got this message. I don't know what it means, but what are you going to do if you're the general of the Orange Army? Something's changed, right? And these first four values, this is the encrypted value of hold, and this is the encrypted value of text. And the same problems we had with the Battle of Midway was that plain text mapped to the same ciphertext repeatedly across messages. We had patterns across messages. So initialization vectors solve that problem. And initialization vectors, its first parameter here, it's a random or unique or different value that is used as input into the encryption in the first block. And because we're using Cipher-block chaining, actually that input will propagate throughout the entire encrypted message. And if we use different IV values with every message, it will obscure patterns across those messages. So Cipher-block chaining, initialization vector, it's all about obscuring patterns and providing that additional layer of information security because we've got block ciphers and because we're going to issue repeated messages that an attacker could observe. Now let's talk about how we generate these. This gets to another tricky part of any kind of security. So we're using AES encryption, we're using CBC mode, we've got some secret key, we're using a random value for our initialization vector, so Derrick, I'm doing everything you tell me to do, finally doing it right? Let's look at it. It's tricky stuff. We've got a 16-byte alphanumeric string as the key. So 128 bits. That's what we need, right? But how many bits of entropy are really contained in 16 alphanumeric characters? Turns out it's only 96 bits, which is only 2 times 10 to the negative 10th search space, what you could have instead of a 128-bit value. It's just, whoops, we didn't quite do that right. It's just tricky. You got to really think about what we're doing. And what initialization vector is really used here? We're using PHP's built-in RAM, same issue if you're doing Java. We give you a 64-bit value. The initialization vector is always going to be 0. Why? You're going to get a warning. The IV parameter must be as long as the block size. Block size is 128 bits. We're getting a 64-bit value. So it says, okay, I guess I'll use 0 over and over again. We tried to set it, and we're still getting, our enemies are still knowing that we send the same message over and over again. How can we do it? And this is, one of the key lessons. You don't have to write this code yourself. In any environment, language, platform, there's going to be some really robust libraries for doing things like, tell me what initialization vector size I should know. I should use. I'm using 128-bit AES. I'm using CVC mode. Just give me the size. I don't even want to know because I might mess it up. And you can even then just give it that size, and it will go ahead and create an initialization vector for you. Getting towards the end here, one other anti-pattern is cross-site request forgery. I think people are familiar with what this is. Half of you? Most of you? I'll give a quick intro to the attack. Cross-site request forgery is an attack because based on the fact that browsers always send cookies to any request to a given domain. So there's a cookie, like your authentication cookie on good.org. Any request to good.org will send along that authentication cookie, even if the code that initiated the request was served by evil.org. So if a user could be tricked to visiting evil.org, they can serve some form that looks something like this with action actually post to good.org/donate. And has 2 parameters. The account is evil.org and the amount is $1,000. So if you can trick the user to clicking on that and they happen to be logged into good.org, suddenly they've unknowingly donated $1,000 to evil.org. Because the browser will happily send along their logged in cookies to here, even though really they were visiting an evil.org webpage. The user probably didn't know that they were submitting this post going to some other domain. So that's cross-site request forgery. Now, a common mitigation against this, this is not the interesting part of our talk. The interesting part is yet the vulnerability. But the solution is, one of the possible solutions is to add a cross-site request forgery token. So we can just generate some random value, and we're going to stick this other hidden field inside of our web form. The idea is that we can stick it there, and we're going to set it in the form, and as well set it in the cookie. Now, the cookie can be sent along in the request, and we can validate that the value in the cookie matches the value set in the form. Good.org can do that. Now, how does that prevent CSRF attacks? It prevents it because an attacker cannot generate this hidden field. They can generate a hidden field, but they can't get the value right. They can't read the cookies on good.org. They don't know what value may have been set. And they can't set any cookies on that domain. So there's no way for an attacker on evil.org to be able to set a cookie on the good.org domain and set the corresponding value in the form. Only good.org can do that. So it kind of proves that request comes from a web page loaded from good.org. Does that kind of make sense? So we're going to generate this random token, yet we've done it wrong. So we'll see how. This is the OWASP recommended way to do it. This general strategy is just the problem is this guy right here, using the built-in PHP rand function. So often I hear people talk about, well, it's secure because it's random, or I'm using a session ID and it's good because it's random. Is random really the security goal we're going for? It's generally not. I mean, for one thing, these are pseudo-random numbers. And here's some Java code, which is actually very similar. In PHP, Java, and many languages and platforms, the default and basic implementation of a random number generator is a linear congruential random number generator, which provides statistical randomness. It's going to provide some uniform distribution of numbers, and when you ask for one, there's almost uniform probability to be any one of those numbers. But it's a completely deterministic process how it generates it. meaning you can actually get 2 repeated values from a random number generator and run this code, just a few lines of code, and calculate the internal seed of the random number generator, the state of the server. And there, moving forward, you can predict every subsequent value that random number generator will output. So these random numbers, they're not secure. There's nothing secure about them. They're statistically uniform in distribution, but they're completely predictable. And any attacker can get 2 values and calculate the internal state generating them. It's very easy to do. So before we go ahead and fix the previous problem, let's look at a little more anti-pattern and help get at the problem. Has anyone ever tried to generate a session ID before? Or you just use frameworks that kind of do it for you, like Cake or Ruby on Rails or something like that? No one's ever tried to generate their own? All right.
Looks like some old code of mine.
Yeah. So I should say a lot of these examples of code I've seen in places and gone in and helped clean up. So we can generate. We've got some user ID. Someone logs in. We're going to use session ID. Store it in our server and send the cookie, and you can look it up and compare it in the future in future requests. So we're going to generate the session ID by concatenating the user ID with a random number and perhaps the timestamp when they log in. So, Derrick, I'm not dumb. I'm going to hash it. Because hashing is one way. The user can't reverse calculate. Calculate the reverse of that. So I'm going to set it in a cookie. Problem is, like we said, random is statistically random, but it's completely deterministic. And time, it's probably not too hard to guess sometimes when a user logs in. And you can actually guess with very high accuracy the internal timestamp of servers. Lots of easy ways to do that. This only provides a few, maybe perhaps 5 or 6 bits of true entropy. And you got a few bits of entropy here, and user IDs are generally not secret, right? So we're hashing this, and yeah, you say, okay, well, I'm hashing it. It makes it harder to attack, but a modern GPU can calculate 2 to the 20th MD5 hashes in under a second. It's nothing, right? It's really easy to attack that. Once the attacker can kind of generate 2 to the 20th of these strings, kind of guessing the time, they know the user ID, and generating different random numbers. Or perhaps, using some understanding of the internal state. You say, okay, well, Derrick, I know MD5s are fast. We'll use something slow like SHA-1, so it takes 10 seconds now. Congratulations, you got 10 seconds before your attack. I'll do SHA-256. Now you take it to 10 minutes. Okay, I'll take SHA-512. Okay, now it takes 10 hours, and you're supposed to attack. Fundamentally done something wrong. What can we do better? Let's go back to the example of our CSRF token. Simply use a library. Starting to see the theme? Don't do it yourself. You use the correct security library in your language. In any language, there's going to be a secure random number generator. OpenSSL random pseudobytes is the one in PHP. And you can tell it how long you want. So this is 32 bytes. I've got a big long number with high entropy. And this is actually the correct way to generate a CSRF token to prevent cross-site request forgeries. And with sessions, don't use them. Use HMAC seriously. I don't like sessions. One, they're really hard to generate secure ones if you're ever writing your own session ID generator, as we saw. Really hard to do securely. And second, why do them at all when you don't have to do a database lookup on every single read to your website? You don't have to do a database write every single time you log in. So HMACs are actually highly performant as well. Even though SHA-1s are slow, they're not as slow as making requests to a database every time. So I love HMACs. They're highly useful, and yet they're not the primitive that everyone thinks about and talks about when you think about security. So, no cargo cult security. We'll identify a true security goal. Are you really trying to keep your user ID secret, or are you really trying to keep the user's information secret? It's probably the latter. We probably want authentication or data integrity when we're trying to do something, when we're trying to, rather than try to provide some secrecy of those IDs. And then once we know our true goal, map that over to the correct cryptographic primitive. Spend some time to learn about it. Obviously, I learn about the modes, the initialization vectors, know what you're doing. I've seen some funny code, or I think people just often write code until it compiles and runs, That's not necessarily the way to make it secure. I see all kinds of crazy stuff. I saw someone for initialization vectors running MD5 hash on the secret and using that as initialization vector. Problem is the same value every time, right? Like they had no idea. They just were just putting some numbers in there until stop getting them warnings. So it just takes a little bit of time to learn about it. Learn about the parameters of the function that you're invoking, and then write as little of your own crypto code as possible. Like I said, in Java, PHP, Ruby, any system, any platform, it's going to be very robust and simple libraries to use to do it. You don't even have to know what size your initialization vector parameter needs to be. Just ask the library for it. Get the library to do it for you. Don't generate your own initialization vector. So here's the correctly filled out table, or as I like to put it, this is my favorite. This is the correctly filled out table. Don't do any of this, or my 5-year-old may come and slap me. So that's it. Happy to take any questions. If you want these, there's a bunch of links on here to cargo cults, and like I said, the original talk where I got some of the inspiration from that table. Any questions? Comments?
Is that table up on your GitHub? Is it linked up there anymore?
Yeah, I think on GitHub I have links to these slides, and on the slides here. Let's see. I think it's.
They're in your slides.
What's that?
They're in the slides. I'm looking at it right now.
Yeah, this is. If you want to see the VeriSign presentation, this is it. I should have named the link better. But it's an excellent talk. They very methodically fill out the table for you, give you kind of the theory behind why HMAC versus public key cryptography stuff. Yeah.
Very good, because I actually have a project with a form field with credit cards that I have to fix up.
Oh, really? Good. So you got to put a CSR token. Is that it?
Yeah.
Good. Yeah. OWASP is great too. Anyone familiar with the OWASP website? So they also have recommended ways you could do in CSRF, and what the attack is and how to mitigate for it. It's very accessible with like non-security experts like me, just application engineers. So. Yeah, if you just Google OWASP, but yeah, I think the leaks back and forth between. There's my cargo cult security if you want to track some of the attacks. Yeah.
So the CSRF, you mentioned trying to get, you'd have to get someone to click on the button.
Uh-huh.
If the attacker can do JavaScript, they can click the button for you.
Yes.
They can post.
You're right. Yes, that's absolutely true.
Or if so this was something. I run a website. It's a message board, and so about 10 or 12 years ago, I was still kind of doing some of this stuff, that not always doing stuff correctly, and I noticed that when you clicked on certain, there was someone who, if you clicked on their message, it would log you out of my site. And it was because they had in their signature, they had an image tag that just went to the logout page for my site.
Okay.
And I didn't have any,
Uh-huh.
I didn't have any kind of token on that to make sure that it was really
that person
that
was
one. And
logging
so
out.
there was no, it wasn't even a post form, it was just, and it was, it didn't hurt anything. It
More
just,
annoying, yeah.
Yeah, it was just annoying, and people were doing other stuff, it had polls, and people would make things that would vote for poll, they put an image that would vote for polls,
Oh, really?
vote, so that they could pad their votes or something,
Yep.
just.
Yeah, it's another one, yeah.
Yeah,
And the problem is, a lot of the, like you mentioned, the sign-up page is interesting because it's GET requests. So the CSRF usually is a problem where there's some state-changing operation on the server. And that's one reason you should never do state-changing operations on a GET request.
Right.
Because it's CSRF, right? They can just put an image tag, any URL in there, and happily go along. But normally if you have read-only GET requests, then they can't damage anything, even if request is made. Who cares? It just has to watch the load your site.
Right.
I do have one of the pieces of slides to hand out.
Another question.
Yeah.
What kind of performance impact do the different modes have?
That's a good question.
I actually looked up that hashing algorithm. It's very small, almost not larger than numbers, and the blowfish obviously will increase the milliseconds by 0.001 or 2. but you can get about 1,000 hashes in before that even starts lagging your system. Encryption in a processor space is not.
So with the CBC,
Yeah, that's what I was like the
yeah,
the CBC and the ECB or whatever it was.
I think a lot of the CB. Well, you don't want to use CBC pretty much ever.
Yeah, CBC is the recommended mode.
But CBC, which has its own problems, but
Isn't that
I
what you
believe
said you wanted to use the CBC.
CBC is the recommended
Yeah.
one.
Yeah.
yeah, CBC has. I mean, there are some attacks that have come against CBC, and they've tried to fix them. But what the modern processors have, if you're using AES, modern processors have AES acceleration features built in.
So regardless of mode, if you're doing
Yeah, if you're using
AES,
if you're using AES, you're pretty much going to be pretty fast because as long as you're using like the OpenSSL libraries that are going to take advantage of those things.
By far, the hardest thing to do is the encryption, not the mode.
Yeah.
So, any
For-
kind of speed up that you're going to gain is by using optimizations of the encryption level.
Now Blowfish is slower, which is why when you're doing like password hashing, you actually want to use Blowfish because you want it to be harder for someone. For encryption, you just want it to be fast, so you can get through because you want to be able to decrypt it quickly. But
Yeah,
when you're hashing, you want it to be hard to make it hard to attack. You want to make it hard to
Yeah,
guess.
we were trying to develop basically hash isn't the right word, but trying to develop a known like sharding effect for like an internal file system. And so we were looking at taking an identifier, and we wanted to be able to both encrypt and decrypt it as quickly as possible. We were not trying to achieve security out of that part of it. We were just trying to generate a known, in effect, a hash, but one that we could reverse. Yeah, and because we were trying to generate paths out of that, and then be able to kick it back. So that's why I was asking. I didn't know if the mode that was getting used, because we were trying to make that as fast as possible. We were not trying to obtain security out of it necessarily. That's why I was asking about the mode.
Good question.
Trying to make it as performant as
I
possible.
don't know.
If you have to decrypt it, it's not going to be much of a hash unless it's a pointer system within a file base. Is that what you're
Yeah,
trying
the
to do?
hash isn't really the right term. I mean, we're trying to generate a known.
Most computers already have AES chips installed within the processor, so that you can't really get any faster than that. On an SSD, I can encrypt and decrypt the drive almost on the fly at less than a nanosecond in most cases.
Yeah, I can just talk at Open West, and I think someone there asked me, well, why do they have those other modes? I don't know.
Some of them are historical.
Yeah,
They just-
that's,
They've come up with better modes, and so they added them, and they just kept the old ones.
yeah.
For example of
the fastest.
So an example of why you don't do the EBC, or don't always do the same initialization vector. I'm not sure which they did, but when Adobe got hacked and the password database got out, it was encrypted. It wasn't hashed, it was encrypted. But no one ever found out. I don't think anyone ever figured out what their key was. But everyone found out what all the passwords were anyway, because the same password always was encrypted as the same value. And then right next to it, they had the password, like their password remember help text that you put in. And so if you had the same password as someone else, and they put something stupid for their text, well, now yours is cracked too, because
Yeah.
they put something that made it really obvious what the what the password was.
Like
And now
the actual password.
Everyone, yeah. So yeah, some people did that, or rhymes with, or people did all sorts of
Sure.
stupid things as their help text, and then that compromised everyone else to use the same password.
So encrypt your help text as well.
Right.
Well, what is the recommendation for storing, data at rest inside of a, MySQL or whatever? Because I typically see people using AES encrypt symmetric style stuff, right? And that thing was saying symmetric for nothing except confidentiality, and maybe that's the goal.
Yeah, if that's your goal, it's great. I mean, Lux disencryption, so we use Elucid. I don't know all the parameters. I didn't set it up, but does anyone know the parameters to Lux? I assume you could set the cipher and everything, but that uses symmetric key cryptography. And,
public key cryptography is generally only used to encrypt a symmetric key, which is then used for the actual encryption.
Yep.
So it's not, symmetric key is used all over the place.
Yep.
It's very robust and fast, and that's what everybody uses, but you just shouldn't use it for stuff it's not designed for.
Yeah, exactly.
The other thing is, a lot of times you want combinations of all these things.
Sure. Yeah.
So, it's not just a matter of picking one thing and that's what you go for. Typically you want several of those so that you cover all of your bases if you want full security.
Yeah. If you encrypt it and have an HMAC, then you have the encryption and you authenticate that it hasn't been tampered with. There's something about what order you're supposed to do that.
Yep, there it is. Yeah,
I don't remember which order.
Encrypt or add the MAC. I don't remember either. It is tricky, right? That's why you look it up, right?
Yeah.
So my question is kind of similar to with recommended solution is I've often wondered if the system gets hacked and I've done my encryption correct for what I'm doing, and the encryption in the system gets hacked, how do you keep the person from not having everything they need to get in anyway? So I've encrypted my database, but the key's right there anyway. So it's like putting my key to my house under the rock. They grab the key and open it up.
So where does that
That's
go
where
to?
asymmetrical stuff comes in handy, because you encrypt with one key and decrypt with another, or public, private.
You basically have to.
If your system's
Really-
cracked, don't they get both your public and private?
It depends
Well,
on
if they're on different
how you
systems,
design
or
it.
it depends on how it got hacked. If your database could get hacked in a way that they get all the data out of the database, but they're not actually on the system. There's all sorts of ways for things to get hacked, and so you have to, where you have the keys. One company I worked for, we had, where we had our credit card stuff stored, and the stuff that could access that, it was all encrypted, and we called it the Holy of Holies, and that was like our, that was where we really, really, really cared about security, and nothing could get in there, and we really made sure that if an attacker got in, they still didn't get that information.
I think a use case is a laptop, right? So if you use your laptop and you have sensitive data on it, if you encrypt your hard drive, usually you have to enter some passphrase when you first boot. You have perhaps multiple volumes. Your boot volume isn't encrypted, otherwise you couldn't boot. You have some other data volume that is encrypted, so you can boot to the point where you can enter a passcode that will, provide the, allow access to the key that then can decrypt the volume. So that way, if you do lose your laptop, even the do boot or whatever, they don't have the passphrase or passcode to be able to get the key that would then decrypt the volume.
Although on that point, I did find a laptop that was really interesting. A Lenovo laptop has a crystal-based password lock. You're only allowed to try and tap computer about 5 times before you are completely locked out, and the password itself is locked within a crystal lattice, and the crystal lattice can only be decoupled by lasers.
Yeah, I don't.
That's how they protected their laptop. You could never get back into the system because of BIOS level protection.
Oh, interesting. Yeah, they do some crazy stuff. I don't understand all the, some of the BIOS and hardware they have. But I do have a little bit of swag. you want. It's actually pretty nice. It's an 8,800 milliamp hours, so it's a big backup battery. You can actually charge 2 devices, 2 phones at once. So how about I give it away to someone who can share the best war story of something they've seen with bad security. If you want to share, you shared one, you're already out.
Magento used to have a bad security hole. See, Magento's main security key is left within a local.xml file within the app system. And they used to have a way of actually accessing that through the images of the admin panel. So if a customer got a way into the admin panel through a non-insetted password like admin, they could post something into the image directory, and the image directory would then access Magento's key system, which then allows you to go completely to the database and unlock everything.
Oh, lovely. That's
Yeah.
a good one. How long ago was that? Or is that recent?
That was 1.6, and we're already about 1.9 in the system. Still pretty it's still, I don't trust it myself as much.
Yeah.
I've been through it a lot.
Well, thanks. Thanks, Miles, right? There you go. It's actually pretty nice.
My favorite is the PS3.
Oh, yes. The key system was an elliptical curve.
They had an amazing amount of security put into the PS3 chips and all this stuff. They had hypervisors and protection at like every level. At the end of the day, and kind of getting back to your question, is everything was essentially protected by a global master key. If you figured out what that global master key was, everything else was worthless. It didn't matter.
And I think that global master key was already within every version of the PS3's firmware. The firmware itself contained the elliptical key to the other keys of everyone.
Yeah. Once you crack that, you have access to every PS3 system on Earth. Period. And that was awesome. I also saw a great one. I went to Black Hat a few years ago. I've been to Black Hat several times, but a couple years ago they were talking about printers that like these corporate printers, big printers that they have websites and cool things.
They got their Wi-Fi's open.
And well, there's that, but there's like websites where you can go to these things, and there's protections where if you have to log in to the printer in order to change certain settings, like make a copy of everything that's copied or printed, send it to this email address. So you have to log in order to change things. But it turns out that their URL scheme was a simple match, and so it's like anything under /admin, if that's part of the URL, then it requires security. Anything else is open. So if you went in to a URL and put /admin, which URL formatting, that's perfectly fine and valid, no problem, it didn't match their required security, and so, oh sure, you can get to that site now. You don't require any authentication for that one. So then you could go in and edit all the settings for the printer, change everything you want, and it had...
You said you could email stuff that had been printed? Is that
So
it?
yeah, you could actually email anything that was printed or scanned or copied or anything on that.
That's fun.
Yeah, that's awesome.
I have another report that takes it a little bit further, where it's a network-driven printer with its Wi-Fi open, and they were able to go through the Wi-Fi to get into the network because it is literally a router.
Oh, wow. That was fun. Well, anyway, thanks a lot. Be happy if you want to connect on LinkedIn or anything like that. Talk to you some more. So.